Hello everyone, today we are going to talk about vectors, but before we dive into vectors, let's first have a look at coordinate systems. In 2 dimensions, a coordinate system consists of a horizontal line, which we call the x-axis, and a vertical line, which we call the y-axis. We divide these lines by adding ticks on them at a regular distance. Let's say that distance is 1, in that case we can number each tick according to the distance between them. If we now add a point, let's call it P, anywhere on this coordinate system, we can assign it some coordinates based on its position. We do that by tracing a line parallel to the y-axis onto the x-axis and a line parallel to the x-axis onto the y-axis. This gives us an x-coordinate of 5 and a y-coordinate of 3. We note these between parentheses. Just for fun, I'm gonna add a point Q, and to calculate its coordinates, we do the exact same thing. We trace 2 lines, and then we get an x-coordinate of -4 and a y-coordinate of 2. Do note that we always write the x-coordinate first and then the y-coordinate. There's also a special point, and that is where the x and y axes cross. We call that point the origin. We often give it the letter O, and its x and y coordinates are 0. Alright, now we are ready to move on to vectors. In contrast to points, vectors do not have a position. We also don't use a point to represent them, but instead use an arrow. Vectors are defined by their length, which can become longer or shorter, and their direction, which is the way in which they point. Since they don't have a position, we can perfectly move the vector somewhere else, and it is still the same vector. I'm gonna give this vector the letter A, and the bar on top of it means that we're talking about a vector. To assign the x and y components of a vector, we calculate how many steps the vector goes left or right, and how many steps it goes up or down. In this case, the vector goes 5 steps to the right. Positive numbers indicate rightward motion and negative numbers indicate leftward motion. The vector goes 3 steps up, and positive numbers indicate upward motion and negative numbers downward motion. The vector's components are written between square brackets like so, with the x component on top and the y component at the bottom. Just for fun, let's also add another vector b. To calculate its components, we take 4 steps to the left, which gives us -4, and we take 2 steps up. We can then write these components once again between square brackets. As I said earlier, vectors do not have a position. However, if we assume that the tail of a vector is sitting at the origin, then we can think of a vector as being a point. Let's quickly have a word about notation. This is a 2-dimensional vector. We write the x and y components between these square brackets. For a 3-dimensional vector, we can add a z component, and we would also add a z-axis which would point outside of the screen. We can expand this vector even further by adding a w component. Now you might be thinking 4-dimensional vectors, wait, what? Well, we'll talk about that in the video about matrices. There's one last change I'm gonna make here, and that is that I'm gonna write these components as the subscript of the vector's name. The reason why we do that is to not cause any confusion when we have multiple vectors. Finally, we can generalize this to n-dimensional vectors. We do that by not using x, y, z, and w, but just counting the components from 1 up to n, where n is the dimension of our vector. Alright, let's now move on to scalar operations. Scalar operations are just operations between a vector and a number. X is the number, and it's also called a scalar, but more on that later. The operation could be a multiplication or a division. I'm gonna continue to explain scalar multiplication, but scalar division is completely analogous. To multiply a vector with a scalar, we just multiply every component of that vector with the scalar. As an example, I'm gonna take a vector a and an x value. We can now fill in these values in our equation and calculate the result of a times x. To clarify these numbers, I'm gonna visualize vector a, and the result of its multiplication with x would be a new vector that is 3 times longer. In other words, this new vector is scaled by a factor of 3, and that is why we call x a scalar. For completeness, if we would have divided by x, we would get a vector that is 3 times shorter. There's a special case in which we multiply with an x value of -1. As you can see, in this case, the vector's components have become the opposite, and the vector itself also points in the opposite direction of the original vector. To simplify this, we just say that the green vector is just -a. Now that we know what scalar operations are, let's move on to vector operations, which are operations between two vectors. This could be either an addition or a subtraction. I'm going to continue to explain vector addition, but once again, vector subtraction is completely analogous. To calculate the sum of two vectors, we just calculate the sum of their x components and the sum of their y components. As an example, I'm going to take two vectors, a and b. I'll fill in their values in our formula, and now we can calculate the sum of a and b. That's all great and everything, but let's actually draw these vectors and visualize the result of their addition. To visualize that, I'm going to move vector b's tail to the tip of vector a. The result of their addition is then a new vector that starts at the tail of vector a and ends at the tip of vector b. For completeness, let's also talk about how subtracting vectors would look. In that case, we would get a vector that goes from the tip of vector b to the tip of vector a. Now, why is this useful? As I said earlier, we can think of vectors as being points if their tail is sitting at the origin. And lucky for us, vector a and b's tail are sitting at the origin, so we can think of them as points. And now you see that we can use vector subtraction to calculate a vector from one point to the other. What's even more interesting is that if we calculate the length of this vector, we know the distance between these 2 points. Talking of length, let's actually discuss the length of a vector. We also refer to it as the magnitude or norm. We represent it by writing these 2 vertical bars on either side of our vector, and in 2 dimensions the length of a vector is defined by this formula. We can extend that to 3 dimensions and even write a version for the generic n-dimensional vector. To understand how that formula works, we're gonna take our beloved coordinate system and take a random vector, in this case vector v. Then I'm gonna draw a triangle beneath the vector, and do notice that I could have perfectly drawn it on top, it's just that I like to draw it beneath it. This triangle is a right-angled triangle. The width of that triangle is the vector's x component, the height of that triangle is the vector's y component, and then the hypotenuse, or tilted side of the triangle, is the vector's length. At this point, we've got a right-angled triangle of which we know the width and the height, and we are looking for the length of its hypotenuse. And lucky for us, there's been a famous mathematician called Pythagoras who came up with the Pythagoras theorem: a squared plus b squared equals c squared, where a and b are the width and height of a right-angled triangle, and c is the length of its hypotenuse. We can now replace a, b, and c with our vector's components and the vector's length. We'll swap the left and right side of that equation. We'll take the square root of either side of the equation, and now we've got our expression for the length of a 2-dimensional vector. If we fill in the components of that vector in this case, we can calculate that this vector's length is equal to 5.83 and a bit. Concerning a vector's length, there is a special case which we call a unit vector. It's also referred to as a normalized vector. We write such a vector with a hat on top of it, and a normalized or unit vector is nothing more than a vector with a length of 1. In fact, we can take any arbitrary vector, divide it by its length, and then the result will be a vector that points in the same direction as the original vector, but that has a length of 1. We also define a few standard unit vectors, being e hat x, which is a unit vector along the x-axis, e hat y, which is a unit vector along the y-axis, and e hat z, which is a unit vector along the z-axis. Using these unit vectors, we can introduce an alternative way to write vectors, and that is to write them as the sum of their components multiplied by the respective unit vector. We call this unit vector notation, and we'll need it in just a bit. But first we're going to discuss 2 ways in which we can multiply vectors. The first one being the dot product, also referred to as the scalar product because its result is a scalar. We write the dot product of 2 vectors as a dot b, and in 2 dimensions it is defined using this formula. We can extend this formula to 3 dimensions, and just like with the vector's length, we can also write a generic version for n-dimensional vectors. To understand the dot product, I'm gonna draw a vector A and a vector B. I'll then draw a triangle beneath vector B, like so, and once again this is a right-angled triangle. The dot product of A and B is now equal to the width of this triangle. However, there is a catch, and that is that I'm assuming that vector A is a unit vector. To explain this further, I'm gonna introduce this alternative formula, which says that the dot product of vector A and B is equal to the length of vector A times the length of vector B times the cosine of theta, where theta is the angle between vector A and B. According to this formula, the dot product will get smaller if vector B gets shorter. It will get larger if the angle between A and B gets smaller. And finally, here's the catch, I've been assuming that vector A is a unit vector, because if it's not, then the dot product will also be scaled by vector A, and it will no longer be the width of our triangle. To dive a bit deeper into how the dot product changes based on the angle between vector A and B, I'm gonna draw vector A and vector B and write their angle next to it. If the angle between vector A and B is 0 degrees, then the cosine of that angle between them, which is 0 degrees, will be equal to 1. This means that we can simplify our formula in the case that theta is 0 degrees, because then the dot product of A and B is just the product of their lengths. Alternatively, if the angle between A and B is 90 degrees, or if it is 270 degrees, then the cosine of that angle will be equal to 0, and therefore we can once again simplify our formula for the dot product by saying that if A and B are perpendicular to each other, then their dot product will be equal to 0. Finally, if the angle between A and B is 180 degrees, then the cosine of that angle is going to be equal to -1, and then the dot product of vector A and B is going to be equal to the opposite of the lengths of A and B multiplied. We can simplify all these formulas even further if we assume that vector A and B are unit vectors. Out of this, we can conclude that the dot product is equal to 1 if both vectors point in the same direction, that it is equal to 0 if both vectors are perpendicular to each other, and that it is equal to -1 if the vectors are opposite. In other words, you can think of the dot product as a measurement for how similar two vectors are. I'm quickly going to come back to the original formula for our dot product, because if we reformulate that a bit, then we can write an expression to calculate theta, which was of course the angle between vector A and B. There's one last thing about the dot product I wanted to show you, which is that the length of a vector is actually equal to the square root of the dot product of a vector itself. I'll leave that up to you to figure out why that is. Let's now move on to that other way to multiply two vectors, which is the cross product, also referred to as the vector product because the result is a vector. We write it as A cross B, and it is defined as the determinant of this matrix. Now, we haven't covered matrices yet, leave alone how to calculate their determinant, so you just have to take from me that that result is equal to this massive formula. However, if you take a closer look at this, you might recognize unit vector notation, which means that we can actually rewrite this formula between our beloved square brackets. Also notice that the cross product is only defined in 3 dimensions. To visualize what the cross product means, I'm gonna once again draw vector A and the vector B. Their cross product is equal to this white vector. Unlike the dot product, the order in which you take the cross product of two vectors actually matters, because if you take the cross product of B and A, you get a vector that points in the opposite direction. So you could therefore say that the cross product of B and A is equal to the opposite of the cross product of A and B. The cross product results in a vector that is perpendicular to the original vectors. You can visualize this using the right-hand rule. If you take your right hand and point your index finger in the direction of vector A, your middle finger in the direction of vector b, then your thumb will point in the direction of their cross product. To show some of the properties of the cross product, I'm going to introduce this alternative formula that says that the length of the cross product of vector a and b is equal to the length of vector a times the length of vector b times the sine of theta, and theta is once again the angle between vector a and b. Another way to think of the length of the cross product of a and b is to think of it as the area of the parallelogram between vector a and b. According to this formula, the length of the cross product will become shorter if vector a or b get shorter. The cross product will also get shorter if the angle between a and b gets smaller. To show why that is, I'm gonna draw once again vector a and b, and I'm gonna display the angle between them. If the angle becomes 0 degrees, then the sine of theta, in other words the sine of 0 degrees, will be equal to 0. The same goes for an angle of 180 degrees. This means that just like with the dot product, we can also simplify this formula by saying that if a and b are parallel to each other, denoted with these two vertical bars, then the length of the cross product is going to be equal to 0. Alternatively, if the angle between a and b is 90 degrees, or if it is 270 degrees, then the sine of theta, or the sine of the angle between a and b, is going to be equal to 1, and therefore we can write another expression that says that if a and b are perpendicular to each other, then the length of their cross product is going to be equal to the product of the length of a and b. Once again, we can simplify all of these formulas when a and b are unit vectors. In conclusion, the length of the cross product is equal to 0 if two vectors are parallel and equal to 1 if two vectors are perpendicular. This means that you could think of the cross product as a measurement of how perpendicular two vectors are. This in contrast to the dot product, which was a measurement for how parallel two vectors are. One last interesting property of the cross product is that if you take the cross product of the vector itself, the result is equal to 0. But once again, I'll leave that up to you to figure out why that is. Phew! That was it! Congratulations, you made it to the end of this video. I really hope you learned something. If you enjoyed this series, then please consider becoming a patron on patreon.com/floatymonkey. With that being said, I'll see you all next time. Goodbye.